Hi folks, welcome to another Lab and Theory tutorial. Today's video is the first of a two-part series that introduces root-finding methods. What are root-finding methods? Simply put, root-finding methods are iterative algorithms that solve the problem f of x star equals to 0. Now, x star is a special point. It satisfies this equality. It's a point at which the equation we're interested in equals 0. Now, why are we interested in these types of solutions? So roots are actually special points, and they come up very often in science and engineering problems. And in part 2 of this video, we'll actually take a look at some applications and where the roots come up and how we can actually use them in real life. And of course, as you saw from the title of this video, we'll talk a little bit after we develop some basics as to how MATLAB's function fzero works. And if you understand how it works, you understand its limitations and its uses, and it makes you overall a better scientist and engineer and a MATLAB user. So let's begin. Again, we're interested in a function such that f of x star equals to 0. Now, the question comes up, why can't I simply solve for it by hand? Let's say we have something like ax squared plus bx plus c, and I set that equal to 0. I know I can use the quadratic formula to solve for x here, and then I can get the answer I'm interested in, or the answers I'm interested in. So why can't I do that for every problem I come across? Well, the truth is, very often, in fact, more often than not, we have equations or functions that are not easily solvable like the quadratic equation. For example, let's take a look at a simple problem. What if I have tangent of x minus x equals 0? And I want to solve for x. I want to know where this function, so this is our f of x, equals 0. This is actually not a trivial problem. And I need to use a function like, say, fzero in MATLAB to find a solution to this problem. Now, let's talk a little bit about root-finding methods, which are algorithms that allow us to solve for roots of equations. We'll look at two classes of root-finding methods. The first class are what are called bracketing methods. The second class are called open methods. Now, before I get started and differentiate between those two classes, I want to talk about one thing, and that's that in this tutorial, we're going to look at one-dimensional problems alone, so 1D problems. What does that mean? That means that I'm going to look at f of x equals 0. So there's one independent variable, not f of x, y equals 0. There are other methods that tackle this type of equation, which is a multi-dimensional problem. So not all methods that work for 1D problems work on multi-dimensional problems. Some do, and we'll look at those, but this is in general a little more involved. It's an extension of a 1D problem, but again, we'll look at that in a little more detail later on. So let's go back. So what are bracketed methods? So bracketed methods. Bracketed methods are a type of root-finding algorithm that brackets the solution we're interested in. Suppose we have a function that, looks like that. What a bracketing method does, so by the way, on this plot, we have two roots right here and right there. So a bracketing method brackets the function, meaning that it identifies a start and a finish, 2 points, where the root lies in between these 2 points right here. And bracketing methods are unique in that, generally speaking, if a function is well behaved, that means the function does not diverge. So what that means is, suppose our function does this, and then it comes back down like that. In this case, of course, the function is not well behaved in this region, so a bracketing method is not guaranteed to work there. We'll talk about that a little bit more later on. So to come back to it, bracketing methods are guaranteed to find a solution or a root to a problem, so long as, number one, it actually has a root, and number two, it is well behaved, meaning you do not see something that looks like this in the function, which makes them very powerful. That means you're guaranteed to find a solution. What's the problem with bracketing methods? Bracketing methods are often slow compared to the other class of method, which are open methods. So what are open methods? Open methods are methods that typically only require 1 point on a function. So again, we have a function that does this. We only have 1 point, so we're not sort of restricted to a region that we know. We just have a single point, and it'll iteratively move along the function until it finds the root we're interested in. What are the problems with open methods? Open methods do not have a guarantee in general to find the root of the function, but on the other hand, they're typically faster. So again, there's no free lunch, there's a trade-off. Bracketed methods are robust in a sense that they'll find the root you're interested in, but they are kind of slow compared to open methods. Now, one small point I wanted to distinguish, which is the multiplicity of a root. What does that mean? Suppose I have a function that looks like this. Notice how there's actually a sign change between the part of the function before the root and the part of the function that is after the root. So the function is positive here and negative here. On the other hand, if I have a very simple function like x squared, for example, there's a root at 0 right here, but the function does not actually change sign. So it's positive on this side and positive on that side. And this is known as a root with even multiplicity, and this is known as a root with odd multiplicity. And you can often see this in polynomials, where if you have a repeating root is of even multiplicity if it repeats twice or 4 times, and is of odd multiplicity if it repeats once, 3 times, and so on and so forth. Now, if we have a root that is of even multiplicity, it often is actually troublesome for bracketed methods to find, because they depend on there being a change in signs to actually sort of narrow down the window and hunt down and identify this root. So again, this knowing a little bit about your function will help you pick the appropriate method to finding the actual root. Now, open methods can deal with even multiplicity roots, such as in x squared, but it does come at a price, which is usually they run a little bit slower. Okay, now, just one last thing to keep in mind is, of course, there are always specialized methods for solving for solving equations, like polynomials. If you have polynomials, we know that for x squared, or a quadratic polynomial, we have the quadratic formula, and we can do different things to deal with special polynomial systems. Other functions that we know a lot about, we can develop specialized methods to dealing with them. But today, we're not going to look at specialized methods. We're going to look at general methods. How do these methods tackle general problems that work for a broad array of functions? Now, let's take a look at bracketed methods. We're going to study 2 methods. The first is called bisection, or the bisection method, which is actually the simplest method we'll start off with. The next is called the false position method, the method of linear interpolation, or regular falsi method. Now, bisection is really the simplest sort of concept you can come up with for a reliable approach, a reliable method of finding the root of a function. So what does that look like? Let's say we have a function here. So this is the y-axis and this is the x-axis. And let's say the function looks like this. The point we're interested in is this point right here. What does the bisection method do? The bisection method starts off with an interval. Now, the interval is specified by the user. So we give it 2 starting points. In this case, we'll start off with a point right here and a point right there. So to visualize our interval, we can think of this as being the interval, this point as being point A, and this point as being point B. And again, this is our interval. The bisection method does the following. Given an interval over which there is a sign change, so this side is negative, and this side is positive. So this is f of A, and this is f of B. So given an interval where there is a sign change, it takes that interval, divides it by 2, so that'll be somewhere right here, and then evaluates the function right there. So now we evaluate the function, and this is our new point. Now, we have to make a decision. Do we change our interval to be between points A and this new point? I'm going to call this new point point C, or B and point C. What the simple logic would tell us is we look at the sign of point C. In this case, point C is positive. And then we choose the new interval to be between the 2 points that have opposite sides, including the new point, of course, meaning that our new interval is now A and this new point C, which becomes B, because the sign here is positive and the sign here is negative. And then we evaluate the function. and this takes us to a new point right there. And then we repeat the process. So again, now this is our new point. But now, in this case, our new point is actually negative, and our old point is actually positive. So our new interval will comprise of this point right here, and point what we called point C. Let's call this point D. And now, if we divide this by half, our new evaluation is right here, which takes us very close, if not right on the root of the function. Now, of course, you repeat this process until a certain tolerance is satisfied. What does that mean? That means either f of x, so x is a candidate point, or the absolute value of f of x is less than some tolerance epsilon, let's say 1 times 10 to the minus 6, or the change between our edges of our interval, the edges of our interval becomes really small. So if delta x, if the change in x gets smaller than some, I'm going to call this epsilon a, and I'm going to call this epsilon b, and let's say this is 1 times 10 to the minus 4, for example. Why is it important to have a criteria like this? Why can't we simply say, hey, when we get really close to the 0 point of the function, let's stop? Because sometimes depending on the slope of the function, this is going to change much slower than this. So our function will actually we're going to start taking really small slices, and we're not going to satisfy the condition that we might have on f of x. In that case, we stop, we know it's good enough, and then we move on. And this is the basics of the bisection method. Again, it's quite a simple method. It's a very intuitive approach, and it's actually guaranteed, if the function is well behaved, to find the root of the function. Again, for a one-dimensional system that we're looking at. There are generalizations to high dimensions, but in this case, for a simple function of one variable, of one independent variable, the bisection method is hard to beat. Again, the only problem with it is it can be quite slow, and the convergence actually gets slower, or the digits of precision you gain actually diminishes as you get closer to the root. The next method is the false position method. This is also known as linear interpolation or regula falsi, the false position method. So what's the false position method? The false position method is actually very, very similar to bisection, but it uses actually a different updating scheme. What does that mean? Suppose we have that same function we looked at last time, where the root of the function is right here, and we've evaluated the functions at, this was point B, and this was point A. So we have our initial interval over here. Now, bisection method says let's divide this interval by half, and then let's select the new point as the midpoint in this interval. What the false position method does instead is says let's connect a line between points A and points B. So it would look like this. That's actually a horrible line, but let's get rid of that. Let's do a little better job over here. Let's say we connect A and B by a line, and then what we do is we evaluate this function at the point where this line intersects the x-axis. So right here, we'd evaluate the function right there. This would be our new point C. So we take that new point, and again, we make a choice of keeping this point based on the signs of B, which is positive, and A, which is negative. Now, C is actually positive here. So in this case, again, we keep A and C. And then we repeat the same process. We fit a line between A and C. And notice how it gets really close very quickly. So we repeat the process, and eventually we get to the root of the function we're interested in. So the false position method, or the method of linear interpolation, is actually faster in general than the bisection method. However, there are pathological cases where the false position method is actually not preferable. That means you would actually prefer to use the bisection method. What would a function like that look like? Let's take, for example, the following. We have a function that looks like this. So there's a very steep derivative, or a sharp change in the function on this side, and a slow change in the function on this side. And let's say our points, our 2 points A and B, are those points there. This is point A, and this is point B. What would this method look like? Well, we would draw a line, and then, of course, the next point we'll evaluate will be somewhere right here, and then we pick this point, we evaluate the function right here, and then we repeat the process. So B stays the same, and we repeat the process. Sorry, I'm not a very good artist, but you can imagine this would actually traverse back. It would always keep point B, but it would actually start traversing very, very slowly until it eventually finds this point. But again, this is really a pathological case where the false position method is extremely inefficient. Contrary, the bisection method, you'll have these 2 points. There's your interval, you divide it by half, and then you evaluate the function there, and then you repeat the process, and then it gets you to the root of the equation relatively quickly. So this is the false position method. And these are the 2 bracketed methods we're going to cover. And now we're going to turn our attention to open methods. Now for open methods, the only open method we're actually going to look at is what's known as Newton's method or the Newton-Raphson method, depending on if you're an engineer or a mathematician. Now, the reason we're only going to look at Newton's method is because it's a classic root-finding method, and it's perhaps the most widely used of all root-finding algorithms. The Newton's method is actually quite simple, yet it's very powerful because it's extremely fast, and in general, it's well behaved. We'll look at some cases where it doesn't quite work really well, but in general, it's well behaved. Now, let's go about deriving Newton's method. Now, Newton's method is the first really sophisticated method that actually involves developing a model. So in this case, we'll perform a Taylor series expansion. Don't let that scare you if you've never done it, but all we're going to do is we want to approximate a function. So let's approximate f of x plus delta x. What that means is I want to approximate the function f at the point x plus some delta x. Okay, so I'm at a certain point along a function, and I just want to approximate the function at some future point given some delta x. So f of x plus delta x is approximately equal to, again, we're approximating it, f of x, so the known value f of x right here, plus f prime of x, so the derivative of the function, times delta x, and then something that is order delta x squared that we don't really care about. Why did I write order delta x squared? Well, if I take a really small step right here, then anything multiplied by delta x, let's say delta x is a number smaller than 1, so if delta x is equal to 0.001, then delta x squared is much, much smaller than delta x, so I can ignore anything beyond this term. Okay, so what I've done is I've created an approximation of f at x plus delta x about the point f at x right here. And my objective is to develop a model such that I can use this approach to find the root of a function where f of x plus delta x is equal to 0. Now, let's define a few things. Again, think about algorithms, these methods as being iterative. So I'm on some iteration n. So n is just how many iterations in I'm in. So again, think of the bisection method, think of the false position method. We take steps, and each step is an iteration, and I'm denoting iteration by the value n. Okay, so in this case, I want to keep this model up here. In this case, xn represents where we are now, and xn plus 1 represents where we want to be in the future. And so xn plus 1 is equal to xn plus delta x, some small step. Okay, now what does that mean? Now let's take a look over here. Sorry about that. So we can rewrite this. F of x plus delta x is equal to f of xn plus 1, right? And we want this quantity, so we want the next step we take to be 0, which is the root of the function. So we set this equal to 0, and that is approximately going to be equal to f of x at n plus f prime at xn, and then delta x. So what is delta x if not equal to xn plus 1 minus xn? So let's plug that in. xn plus 1 minus xn. Now, let's solve for xn plus 1, and that'll tell us, that will kind of define for us an iterative scheme that we can use to actually solve or attempt to solve for the root of an equation. So let's do that. So let's move this over to the other side, divide by f prime xn, and then solve for xn plus 1. Again, this is simple algebra. So on the right-hand side, or the left-hand side, sorry, we will have negative f xn equals, and then we'll divide by f prime xn equals xn plus 1 minus xn, and then finally that gives us, I'm just going to kind of switch these around, sorry for the mess, xn plus 1 equals xn minus f xn divided by f prime of xn. And now this is it. This is Newton's method. So this is the iterative scheme that Newton's method uses. What we did is actually very simple. We built a model, so an approximation of a general function f of x, which is unknown to us. And by performing a Taylor series expansion, we actually obtained a formula that allows us to iterate and find the root of a function. So what's distinctly different about Newton's method than other methods we looked at? Well, first of all, we require only one previous point, so 1 point as opposed to 2 points in the bracketed methods. And we also need additional information, which is the derivative of the function at point n. So again, think about this. So there's no free lunch. We'll end up with a faster iterative scheme. We'll take a look at that in a little bit, but at the expense of requiring a little more information about the function. Now, what does this actually look like graphically? What are we doing here when we use this iterative scheme? So again, let's draw a plot and let's think through this. Suppose we have a function that looks like this. Okay? So again, this is x, this is y, and we're at this point right here. So this point right here is xn. And of course, this is f of xn. What this is saying is the next step we take, the next point, x of n plus 1, is x of n minus this f of xn divided by the slope, f prime of xn. And the slope is simply this right here. And what this iterative scheme means is we're simply drawing the derivative. So we're assuming this function has a linear derivative all the way through in our model, and then identifying this point right here, and then evaluating the function at that point, and this is our new point. Notice how much quicker that is. By taking this derivative step, it actually allows us to take much bigger steps and get much closer to the root, where bisection would require many iterations for it to eventually get to the same level where we got to in just a very simple step. I know this graph got messy, guys, but hopefully the message is clear that Newton's method takes much more intelligent steps and allows us to get closer to the root much quicker. So this is Newton's method. Newton's method uses the tangent of the function to find us a good approximation. So this large jump that we saw right here actually gives us what's called quadratic convergence. What that means is the error that we gain, or the error that we lose, decreases between one step to the other is proportional to the square of the previous error. Basically, that means the number of significant digits, or the number of digits that we refine each step we take, actually approximately doubles every iteration, which is phenomenal. Okay, so why would we not use Newton's method, or when should we be careful? Again, there are pathological cases, and here, let me show you one of those. So suppose we have a graph right here, and suppose the graph looks like this. Okay, now let's say we start right here. The derivative of this function at this point kind of shoots out over here, and then this puts us somewhere down here. And then the derivative at this point shoots out somewhere over here, perhaps even further out, and that puts us somewhere right here. And notice how we can oscillate back and forth and back and forth and back and forth. And there are scenarios where Newton's method is not stable. In fact, there are other scenarios where there's a function, for example, that's quite hilly, like this, that could cause us, suppose we're right here, that could cause us to overshoot wildly and then end up in this entirely unstable scheme. Now again, we mentioned how Newton's method, which is an open method, is not guaranteed to find you a root. But what it is advantageous for is that it's fast. Now, my closing remarks for this video is that Newton's method is actually modified very often to actually accommodate scenarios like this, like the ones we looked at over here. But those are beyond the scope of this video. This is an introductory video into root finding methods, and so we're not going to talk about those. But what we will do in the next video, if you will stick around, is we will actually code up the bisection method, the false position method, and Newton's method into MATLAB, and we'll look at how those work. And my final closing remarks actually talks about the method fzero that's built into MATLAB. You might have come here, watched this video because that was the title. I hope I didn't mislead you, but let's talk a little bit about what fzero does. Now, fzero uses what's called Brent's method. Brent's method. This is named after Brent, who came up with the method. Now, Brent's method is actually clever. It's a bracketed method, meaning that it is guaranteed to find you the root of a function so long as there's a sign change, meaning that if you actually pass in simply x squared, it will actually fail to find the root. We'll take a look at that in the next video and see the limitations of Brent's method. But what it does is it actually switches between bisection, which is a very stable, well-behaved, robust method, but a little bit slow, and some linear interpolation. And then it uses something else, what's called inverse quadratic interpolation, which is basically fitting a parabola to a function, but instead of fitting, y equals f of x, it takes the x data, switches the position with the y data, fits a parabola to it, and then approximates the root that way. Again, this is not to go to the level of exhaustiveness to cover every single method out there, but just to kind of talk about stuff. So fzero uses a combination of the bisection method, linear interpolation, and an inverse quadratic interpolation to identify the root of a function in a stable manner. Of course, it swaps between those methods depending on what a certain criteria it has built into it and what it thinks is actually the most robust method at the time over the course of an iteration. So again, this video will stop here. The next one will code up a few methods in MATLAB. We'll look at the behavior of fzero. We'll talk about some pathological examples, and we'll try to solve one or two science and engineering application practical problems. I hope you folks found this video useful. If you did, please give it a thumbs up. If you want to follow and watch the next videos in this series or another series, please subscribe. Leave a comment down below if you're interested in seeing us work through a problem of interest to you or to someone you may know. And once again, thank you very much for watching. Until next time.